Suppose you have some function that is defined in a few different points. So let's just say that it has some values. It doesn't really matter what they are. I'll just make up a few. So let's see, make one negative, kind of like this. Okay, so we know the value of a function at those 4 different points. And let's name them. So I'll just name this one A, B, C, and D. And what I'm going to do is I'm going to just find all the differences. So let's say I want to find the change from A to B. Well, to go from 5 to 2, that's a change of -3. And if I find the change from B to C, well, going from 2 to 6, that's a change of 4. And the change from C to D, well, 6 to -3 is -9. And going from D back to A, I'm going from -3 to 5, which is a change of 8. So what I'd like you to notice is if I add those all together. So I take the change from A to B, plus the change from B to C, plus the change from C to D, plus the change from D to A. Those all add up to 0. And what I'd like you to see is that that is not special based on the numbers I made up. That has to happen by the very fact of how we're doing this. So this is a property of the procedure, not a property of physics or anything else. Okay, so if you want to see why this has to work out, well, delta AB is just B minus A, and delta BC is C minus B. So if I just write out all of these differences, then I've got D minus C, and then for this last one I have A minus D. Okay, so you can see just pairing up the terms, I have -A and positive A, I have B and -B, I have C and -C, and then finally I have D and -D. So they just explicitly add up to 0. There was nothing special about the numbers I made up. Those were bound to work no matter what they are. Okay, so it has to come out to 0 just by the fact that we're adding up all the differences in a loop. Essentially, we found the difference from A to A, which is going to come out to 0. Okay, so another situation where this idea occurs is if you were, for instance, going out for a run. So I am not a runner, but for people who like to run, you probably find that it feels better to run downhill than uphill. So you might try to come up with a path where you go downhill the entire time from your house and end up at your house. Well, it turns out that's not possible because as you go downhill for one part of the run, you'll have to run back uphill to end up at the same elevation you started at. Okay, so the same thing happens here. Even if for part of the path you're going to a lower value, later on you're going to have to go to a higher value in order to end up where you started. Okay, so what does this have to do with physics? Well, if instead of just having arbitrary numbers that are defined at different points in space, let's say that I have an electric circuit. And maybe for my electric circuit, I will have a light bulb up here, and then maybe another light bulb over here, and then perhaps another battery, like this. Okay, here's a circuit. And let's say that I define this point to be A, this one to be B, this one to be C, and this one to be D. All right, so I can measure electric potentials at different points around the circuit. Okay, so I can measure a potential at A and B and C and D. And keep in mind that the actual values of the potentials don't matter. They're totally arbitrary, but the differences are real. So I can use a voltmeter and let's say connect from here to here and measure a potential difference between those. Okay, and so if I do that, if I take delta V from A to B, and I take delta V from B to C, and I take delta V from C to D, and delta V from D back to A, they have to add up to 0. It's not even physics, it's just math. That, if I'm taking all these differences around a closed loop that begins and ends at the same spot, those differences have to add up to 0. It doesn't matter what's in the circuit. It doesn't matter if there are batteries or light bulbs or resistors or capacitors or diodes or any other component you've never heard of. It will always be true that adding up all the potential differences in a closed loop is going to add up to 0. Okay, so to write that out, if I take the sum of delta V's around a loop, then they add up to 0. Okay, so this rule has a name. This is called Kirchhoff's loop rule. Right, so previously we saw Kirchhoff's junction rule. This is Kirchhoff's loop rule. Those are the only two rules, and you'll be able to solve lots of very complicated circuits by just using those two rules. They're always true. Sometimes they are more useful than others, but our basic approach to solving electric circuits is really going to rely on those two rules.